Welcome to this session on the development of models in research methodology. As a zoology student, you will often study complex biological systems, from ecosystems to cellular processes. Understanding how to build and use models is an essential skill that will help you cut through the noise of the real world and uncover the hidden rules governing nature. Let us dive in and see how this works. To begin our journey, we must first acknowledge a fundamental problem. The real world is incredibly messy. Whether you are observing animal behavior in a forest or measuring physiological changes in a lab, you are looking at a system filled with millions of interacting factors. If you try to study every single variable at the exact same time, you will quickly become overwhelmed by the sheer chaos of the data. This complexity makes it practically impossible to understand how specific things relate to one another without a strategy to simplify what we are looking at. Now that we understand the problem of complexity, let us look at the solution. Imagine you are planning a road trip. You use a map or a GPS application. That map does not show every single tree, pebble, or pothole on the ground. Instead, it is a highly simplified version of reality that only shows the critical information you need, like highways and cities. In research, we do the exact same thing. We create models to strip away the unnecessary details, allowing us to focus entirely on the specific variables we actually want to study. Building on that analogy, let us establish a formal definition. In research methodology, a model is defined as a systematic, theoretical, and simplified representation of a complex real-world system. Think of it as a conceptual bridge that connects abstract scientific theories to the observable empirical data you collect in the field. A well-developed model explicitly identifies the key variables involved in a phenomenon and clearly states the logical or mathematical relationships between them. It is the blueprint that guides your entire scientific investigation. So, we've defined what a model is, but how do we actually use it? Researchers rely on models to structure their thinking before they even begin an experiment. By defining the relationships between variables, models allow us to formulate clear, testable hypotheses. They act as a structured framework that guides the design of your experiments or surveys. Ultimately, your model dictates exactly what data needs to be collected and how that data should be analyzed to answer your core research question, preventing you from gathering useless information. This structured approach leads us to a crucial question. Why is the development of models so important? The greatest power of a model is that it allows researchers to make predictions and test scenarios without having to manipulate the real world directly. For example, economists build models to predict inflation based on interest rates, which is much safer than changing rates blindly. Similarly, epidemiologists use models to predict how a virus will spread, allowing governments to plan hospital capacities months in advance. Models let us look into the future safely. While we have discussed models conceptually, it is important to know that models come in different forms. They can be physical, like a miniature wind tunnel model of an airplane, or conceptual, like a flowchart. However, the most powerful models in quantitative research are mathematical. A mathematical model translates real-world relationships into precise algebraic equations. The most fundamental and widely used mathematical model in research is the simple linear regression model. This model assumes that one outcome variable is directly influenced by another predictor variable in a straight-line relationship, plus some random noise. Now that we understand the concept of mathematical modeling, let us look at the actual equation for simple linear regression. This formula comes from the idea that an outcome is based on a starting point, a rate of change, and some random variation. Y represents the dependent variable, which is the final outcome you want to predict. X is the independent variable, the factor you are manipulating. Beta 0 is the y-intercept, representing the baseline value of y when x is exactly 0. Beta 1 is the slope, telling us how much y changes for every 1 unit increase in x. If beta 1 increases, the independent variable has a stronger effect. Finally, epsilon represents the error term, accounting for all the invisible, unpredictable real-world factors that affect y, but are not in our simplified model. Before we move on, let us see this formula in action with a concrete example. An agricultural researcher wants to predict crop growth based on fertilizer. We are given a baseline height of 10 centimeters without fertilizer, so beta 0 is 10. The crop grows an additional 3 centimeters per kilogram of fertilizer, making our slope, beta 1, equal to 3. The farmer applies 4 kilograms of fertilizer, so x is 4. Assuming perfect conditions, we set the error term epsilon to 0. We substitute these values into our linear model. We multiply 3 by 4 to get 12 centimeters of extra growth. Adding the baseline of 10 gives us a final predicted height of 22 centimeters. This shows how the model simulates a real-world scenario to make actionable predictions. Now that we have used the basic formula, let us look at a more realistic example that includes the error term. An educational researcher predicts exam scores. The baseline score for 0 hours of study is 30 points. Every hour studied adds 5 points. A student studies for 6 hours, but falls sick on exam day, costing them 8 points. We plug these into our model. Beta 0 is 30, beta 1 is 5, and x is 6. The sickness is an unmeasured random factor, so our error term, epsilon, is negative 8. We multiply 5 by 6 to get 30 points from studying. Adding the baseline gives a theoretical perfect score of 60. Finally, we subtract the 8 points of error. The final predicted score is 52. This proves why the error term is critical. It acknowledges that our math cannot perfectly capture the messy real world. Having calculated the error term mathematically, let us now visualize what this looks like on a graph. Here you are seeing a standard linear regression model graph. The horizontal axis represents our independent variable, x, and the vertical axis is our dependent variable, y. The straight diagonal line represents our theoretical model's predictions, starting from the y-intercept on the left. The black dots represent actual real-world data points. Notice how they do not sit perfectly on the line. The vertical dashed lines connecting the dots to the main trend line represent the error term, epsilon. This diagram beautifully illustrates how the model captures the general trend while the error term accounts for the natural deviations of the real world. We have covered a lot of ground today, so let us summarize the key takeaways. First, remember that models are essential tools that simplify the chaotic real world, allowing us to focus on specific variables. Second, they serve as a vital bridge, connecting abstract scientific theories to the actual empirical data we collect. Third, mathematical models, like linear regression, translate these relationships into precise equations, enabling us to test hypotheses and predict future outcomes safely. Finally, never forget the importance of the error term, which acknowledges that no model is a perfect replica of reality. You now have a solid foundation in how models are developed and used in research methodology.